Good afternoon, everyone. I am Rito Kaur. I am a research scientist at Adobe Research, and I will be presenting our work on selection and ordering of linear online video ads. So it was a joint collaboration between INSEAD. Paolo is my advisor from my PhD days, and so with that, let me present you first the definition of linear ads. So these are in-stream ads which comes before, during, and after a video which is watched by a user. So primarily it started out with online publishers like YouTube, Dailymotion, Hulu. Subsequently it came into social media like Facebook and Twitter, and now it is there in gaming consoles like Xbox, and finally of course it is there into mobile phones. Now the motivation of working on selection of linear ads came to me almost 2 years back when I was trying to watch the Steve Jobs 2005 commencement address at Stanford University. So the moment I pressed play, so this is how it started out.
Directly to the forehead. Head on. Apply directly to the forehead. Head on. Apply directly to the forehead. Head on. Available at Walgreens. Head on. Apply directly to the forehead. Head on. Apply directly to the forehead. Head on. Apply directly to the forehead. Head on. Available at Walgreens. New from the makers of Head On. Introducing Activon. Arthritis pain? Activon. Apply directly where it hurts. Activon Arthritis. Available at Walgreens.
So my immediate reaction after this was to quit. Go on the web and find another website to actually watch this. Now, what we saw here is that if the ad is so bad that it actually gives you a headache, you actually move away from the website. And that's an externality, a negative externality for the publisher. Now, my next question was, are the publishers really aware of that? So let's look at the history of the evolution of linear ads. So it started out with non-skippable ads, which is still the most popular format. Hulu came out with selectable ads, where you select one of the 3 ads to actually proceed with the video. Eventually, YouTube came out with skippable ads, where you thankfully can skip the ads after 5 seconds. And finally, you have to subscribe videos, where you have videos without any ads at all. So the bottom line is, there is some negative externality that ad imposes on the continuation of the video, and publishers are aware of that. So that formulated my research question about understanding the retention for ads in online videos. So the idea is, if a user actually exits during an ad, then the publisher cannot show the subsequent ads in the same video and lose revenue on the table. So we wanted to come up with an algorithm that maximizes the publisher revenue by allocating ads not only based on price, which is the market practice, but also some measure of ad quality. But you should keep in mind that when you are talking about ad quality, we are not really talking about the quality of the ad. We are talking about the retention power of the ad. So with that, let me take you over to how the data is generated at the back end. So when you request a video, what really happens is it creates a playlist. It creates a playlist where it creates slots in which you can put the advertisements, and then you have video segment 1, video segment 2, and so on. So at the back end, when you play the video, you have a pod start, and similarly you have a pod complete, and so on for the rest of the pods. And you also have pod progress. So basically, each of these pod start, pod complete, pod progress, these are all events. So when you have the log data, it basically have, for 1 month of data that we used, we had 1 billion events per day. That doesn't really mean that we had 1 billion movies or video sessions. It means we had that many. A particular video session can have multiple events. The size of the total data was around 10 terabytes, so we used Amazon S3. We put some filters to choose what kind of users we want to look at. So we looked at users who had at least 10 sessions per month and a maximum of 20 sessions per day. So with that filter, we came down to 650,000 users and a total of 3.5 million video sessions. And we selected 19 ads out of those video sessions because those are the only 19 ads on which we had complete information because of confidentiality reasons. The reason we looked at so many users was to see how actually the retention of ad affects and what is the contribution of slots on ad continuation. So the next diagram or the graph is actually the crux of our algorithm. You can see that you have one pre-roll, you have multiple mid-rolls, and you have a post-roll. And what you see here are continuation rates. So what is a continuation rate? So if all users have seen 100 pre-rolls and they have exited on 80 of them, their continuation rate is only 20. So that is what we mean by continuation rate. The interesting feature of this graph is you can see that pre-roll is actually less engaging than the first couple of mid-rolls. One thing to note here is there is a selection issue because it's kind of a conditional probability, if you will, because the person who reaches mid-roll 1 must have survived the pre-roll. But even then it's exciting because one would think that pre-roll is the most engaging ad slot for a publisher, but it's not according to this data. So before I get into the modeling aspect, let me define a few things. BI is basically the bidding price for ad AI, also commonly known as cost per 1,000 impressions or CPM. CI is a measure that we create, which is the continuation rate of ad I, which is to say that what is the probability that a viewer watches an ad completely and moves to the rest of the video. And finally, we have lambda j, which is slot specific, which is what I showed you in the previous graph. This is saying that irrespective of the ad quality, every slot has some continuation rate which affects the progression to the rest of the video. Now, the current system is for each video, ads are selected and ordered primarily based on price. And what we are suggesting is, let's select the ads based on a combined measure of CPM and ad quality and through a global optimization technique. So in our model, we go through 3 steps. The first step is calculate the continuation rate for each ad, which is kind of the quality measure. Next is build a combined measure of price and quality, a collective measure. And finally, use a dynamic program to select and order the ads. Now, in this particular presentation, I will not be covering how to calculate the continuation rate. This, you can use any technique you want. You can use statistical models. You can use click-through rates. You can use bounce rates, depending on what kind of application you are doing. But I will be, if you want, actually I'm presenting tomorrow at the RecSys TV workshop on how we calculate this continuation rate. You are more than welcome to come there. So before I get to the actual model, let me show you how we are actually calculating the revenue in this kind of collective measure. So let's suppose you have 3 ads. You have the continuation rates of those 3 ads. You have the prices of those 3 ads. And these are the slot specific continuation rates. And let's suppose that the allocated sequence is A1, A2, A3. That in a video session, you will start with the first ad, followed by the second, and then the third. So the way the revenue is calculated is you have the price from the first ad. The probability of continuing is C1, but it is also affected by the slot specific continuation rate, which is lambda 1. Now, what you get here is from slot 1, this is the expected revenue. Now, if you move to slot 2, similarly you get B2, C2, lambda 2, but it is further affected by the continuation rate of the first ad, because your attitude towards first ad is going to affect your attitude towards the second ad. Similarly, for the third ad, in addition to B3, C3, lambda 3, it is further affected by now 2 of the first ads, C1 and C2. So you get the idea. So if you have to generalize, this is how it will look like for the last ad. And this is what is known as the cascade continuation rate, and also popularly known as the Cascade framework. So with this, let me present to you the maximization function. So for slots 1 to j, we have the price of the ad, we have the continuation rate of the ad, we have the slot specific continuation rate, and finally we have the cascade probabilities. And of course, whether an ad can be selected in your algorithm is kind of constrained by target. So what is a target? When an advertiser approaches a publisher, it tells the publisher that you have to show 1,000 impressions of my ad. So if you show ads beyond the target, you cannot capitalize on the revenue at all, even though that might be a good one. So next, once again, go back to the slot specific graph that I showed you before, because this is something on which we will build our model. But before we go to this, we will actually simplify this. We will simplify this by this diagram. We are assuming here that the slot specific continuation rates are monotonically linearly decreasing. Okay, so we make two further assumptions which are true for the publisher for which we have the data. In each slot, only one ad can be inserted, and once an ad is selected, it cannot be selected for the rest of the video. It may not be true for many publishers, but it's quite true for most of the publishers that we have worked for. So what is the complexity in Cascade framework? So if you have to select J ads for those many slots from N ads, this is the revenue that I showed you. The problem is the computation time for ad selection grows exponentially because you have to try out all different combinations to see what gives you the highest revenue. And it grows exponentially with number of slots and number of ads in the inventory. To give you an idea, if you have to choose 3 ads from 100 ads, it involves more than 100,000 combinations that you have to look at, and it will take you more than 1.5 hours. So imagine trying to watch a video and waiting for 1.5 hours to actually the video to begin, which is impossible to implement, right? So you can get more idea on cascade modeling from these 2 papers. We have extensively borrowed from them, but they have mostly worked on search ads, not video ads. So the main idea of this, how to tackle this, is to eliminate combinations. So even before you actually run it real time, how can you eliminate combinations? So let's start with an example. Let's say you have only 2 ads, and these are the features of the ad. And let's say the optimal sequence is A1, A2. So the revenue is going to come from this structure as I explained before. Now let's suppose the suboptimal sequence is A2, A1, which is obvious. The revenue is R dash. So if R is optimal compared to R dash, this will hold. So if you plug back the values of R and R dash, what you get is this particular relationship. So something is very unique about this relationship. So if you look at this one, other than lambda 2 over lambda 1, everything to my right side is confined to ad 1, and everything to my left side is confined to ad 2. So if by any magical method I can eliminate this lambda 2 over lambda 1, I can generalize this descending order and I can eliminate quite a few combinations. But the hurdle is I cannot do that because this is slot specific, and I cannot do that before assigning it to slots. So this is where we take our first leap of assumption. We assume that slot specific probabilities are linearly decreasing. So that helps us how? Because now lambda 2 over lambda 1 is a constant. We plug it back, and that gives us this nice descending order. So now you can see that everything over here is confined to ad 1, and everything over here is confined to ad 2. So the way it helps is now we can generalize it. We can extend it to N ads. And once I extend it, I define this particular thing as adjusted CPM. It's called adjusted CPM because it has the price, but it also has the quality measure built into it. So this is what we use as the combined measure of price and quality. Okay? Now the question is, why is this decreasing order helping us? Right? So let's look at examples with real numbers. So you have 3 ads to choose from. So you have to select 2 ads out of this 3. And what I do is I calculate the adjusted CPM for each of these 3 ads. So these are the adjusted CPM from the formula that I have. And you can see that I have already arranged them according to the decreasing order. So the possible combinations are all of these 6. And the decreasing order is A1, A2, A3. So the way the decreasing order helps is it eliminates combination. We know that from the decreasing order, A3 cannot come before A1. So with that logic, even before the selection is made, even before we get to real-time application, you are eliminating half the combinations. You have already eliminated half the combinations. But the problem is you still don't know which of these 3 is giving you the highest revenue. So for that, we move to our dynamic program. And in the dynamic program, we use a backward recursion. So we start with the 3rd ad. We consider the 3rd ad in slot 2 and try to find the revenue. So if you consider the 3rd ad in slot 2, what you get is the revenue from the revenue calculation I showed you before. Price times continuation times slot specific continuation, you get this. Your alternative at this point is to not show any ad, because since you're doing a backward recursion, you're not looking at ad 2 and ad 1. Your alternative is 0, not showing any ad. So you take the max of that, and of course 7.84 is greater than 0, so ad 3 becomes a viable candidate for slot 2. You assign that a value of 1. So similarly, you go for ad 2, and you can see you get generate 7.8, but you are generating more over here. So what you do is you do not select ad 2 for slot 2. And you assign the value 0, saying that it is not viable for selection. With similar logic, you move ahead and you assign the value 1, because this is generating more value than what you accrued at the level of the 2nd ad. Now when you come to the 3rd ad in the 1st slot, once again you have this, but you have nothing in this slot, because once again you cannot select add 2 over here or add 1 over here, because that will break the descending order. So once again the alternative is 0, it is generating more than 0, it becomes viable for selection. Now the interesting thing happens when you go to add 2 in slot 1. You generate this expected revenue from add 2 in slot 1, but now you also have the revenue from the slot 2 and add 3, which is further affected by the continuation rate of add 2. So overall you generate 14.6, which is greater than 8.82, so you assign the value 1. So now you get the idea of how we are calculating the revenue at every step. Right? So what you get from here is a bunch of 1s and 0s. You still don't get the selection. You get which ads are viable for selection for which slots, but not actually the selection. So we start with the 1st ad, because that is at the top of the descending order. And we select that, and once that is selected according to assumption, there can be no other ads in slot 1. And you cannot put add 1 in any of the other slots. So once that goes out of the picture, you have 2 ads. But you can see that add 2 is not viable for selection, so you end up selecting add 3. But now it is a very, very toy example with only 3 ads and 2 slots, so that's why we formulate it with a backward recursion formula, which is this one. Okay, so now let's actually go back to what we had. We started out with this, but actually the scenario is this. So what we do is, in the first step, we do a 2-step heuristic algorithm. In the first step, we run the dynamic program where it is linearly decreasing. That is in the mid-roll. Once you have done that, we eliminate all the ads we have selected here and select one ad from the rest of it for the pre-roll. And then from the rest of the inventory, we select the one with the highest price for the post-roll, because there is no other ad after that. And then we repeat that. This gives us the sequence, and we repeat it over all different combinations of n minus a. So now it brings me to our simulation. So what we did was we we assume that a publisher needs to design ad allocation for 50 video sessions. It will have 5 slots. Only one ad can be inserted. So we had a total of 250 impressions. We got from the data that alpha, which is the linearly decreasing factor, as 0.8, and we drew from a normal distribution. So if our draw was greater than or equal to the continuation rate for the ad, we assume that the viewer is going to exit. So, and we ran each simulation 100 times, and we compared 3 different models. So the first model is what we practice in the industry, ordering by CPM and selecting the top J. The second one is sorting by adjusted CPM and selecting the top J. And finally, we compared our algorithm with the rest of it. And you can see the results here. So what is interesting about the result is sorting based on adjusted CPM does the worst. And the reason for that is what we are actually doing when you're doing a collective measure is you're doing a trade-off between price and quality. But the problem is if you're doing just sorting by adjusted CPM, the trade-off is not changing. But in the dynamic program, what is happening is you're starting with the more retentive ads, and as you move along the session, you're looking towards more monetizing ads. So you're continuously changing your trade-off. So the way it helps us is our algorithm was generating 9% more average revenue than sorting by CPM. And the reason why it was happening was not because it was having pricey ads, but mostly because we were able to show more ads because of retention, because of more retentive ads than what we are doing in CPM. So that brings us to our next simulation, that whether dynamic programming is actually needed. So what we did was we varied the price between 100 and 500 and the continuation rates between 0.5 and 0.95, and we had 4 and 5 slots, and let's say the inventory is really low, 20 to 25 to 30. We ran the simulations and these are the results. So let's focus on just the last row. So last row is saying you have 30 ads and you have 5 slots. So you can see that if you enumerate over all combinations, you get a revenue of 836. We do slightly bad, around 3% less, because ours is a suboptimal algorithm. But what we gain is in actually the runtime, because this is 1.5 hours and this is less than 1 second. Okay, so we tried to see that how much can we scale it. So that brings us to our last simulation. We show that if you increase the number of slots from 2 to 7 and you increase the number of ads from 500 to 1500, you're still less than 1 second. You're probably, if you're looking at 200 millisecond as the industry standard, then probably you can still choose, let's say 5 ads from at least 700 ads, which is still a great leap from where we were. So that brings us to my conclusion. What we have shown here is that publishers can increase revenue by accounting for ad externalities. Viewer retention is tremendously increased, and finally, this particular algorithm can be generalized for any digital ad platform with some modifications. But of course, there are a lot of things that we have to take care of. We are already working towards how to take care of this externality of ad if a viewer is watching multiple sessions at the same time, because we are only doing it for one session. Secondly, how to relax this linearity assumption for slot-specific continuation rates. And finally, our target is actually not getting into the optimization function, it is just constraining it. But there are some linear programming and dynamic programming work already there which are looking at how to incorporate target inside the maximization function. With that, I would like to take your questions.
So thank you, Rito, for the presentation. Are there any questions? Well, I will start with one question. I see that in this allocation procedure, you are not taking into account, let's say, the popularity of the video. So I was wondering if, if a video is important for the user will be more willing to watch the ad. So the continuation rate of an ad could vary based on the video. What do you think about this? Are you planning to take this into account?
So, great question. The answer is yes and no. The reason it is yes is when we are calculating the ad continuation rate by the method that we are calculating, we are actually controlling for the type of video, the type of ads, the time of the day, and things like that. But we are not really doing a contextual matching in this case. So that part of the answer is no. But when you're actually requesting the video, what really happens is you know the genre of the video, and based on the genre, we know the continuation rates of ads based on that genre. So you know the continuation rates based on that kind of video. So that kind of takes care of the problem to some extent, but not completely.
Thank you. Other questions? Oh, there's one there.
Yeah, if you were to have skippable ads,
Yeah.
could you use that information and not just use CPM, actually do that in this model, you think?
We are actually trying to do that right now. It's prohibitively expensive in terms of time, and this dynamic program literally goes out of the window because you cannot do this. But there are other approximation methods which have been explored in the past, and we are actively working on that. But it's true that you cannot implement this if you have skippable ads or ads being repeated in the same video.
Are there other questions? So we have time for one more question. Oh, up there.
My question about the user experience, how would you reflect the user reaction about the ad? And if you would incorporate like features of the user or what the user actually would like to watch, how can you incorporate that in this model?
Okay, once again, that is kind of absorbed in the continuation rates that we calculate. So in the continuation rates, we have some habitual parameters from the users, like how many times the user watches this kind of video, how many times a user has watched this particular ad in the past, generally what is the exit rate for the users when ads are shown. So all these factors are actually absorbed into the continuation rate the way we calculate for each ad. So
thank you again, Rito, for the presentation.
Thank you, my pleasure.
So can you guys hear me? Thanks for the introduction. Actually, you pronounced the name correctly. That's very real. So, okay, so there are more people staying than I expected. So anyway, thanks for staying. So I know it has been a long day. I know it's very exhausting. So trust me, I know that better. So in order to make you feel better, so let me share with you my miserable story. So last night we had a dinner, right? That was really nice. So after dinner, I feel so nice. I just stroll along street and enjoying the beautiful night scene and feel the little breeze. I feel real nice. So when I get to the hotel, I took a shower and lay down. So then I started to thinking, so what's the purpose for me to come to Vienna? So I suddenly realized I'm going to give a talk tomorrow, and I have not started working on slides. So that was pretty bad. So okay, so I got totally awake. Then like okay, I just started to work with the slides. I was very lucky. I got it done by this morning, and actually I have enough time to do a couple of dry runs myself. So okay, that's it. So okay, so let's start with the real subject. So my name is Qizhao. So I'm a PhD student from University of California, Santa Cruz. So today my topic is about e-commerce recommendation with personalized promotion. So what is the recommend system? Recommend system most times works by predicting items user will be interested in buying and by using the information know about the user. But for example here, you purchase oatmeal and butter from an e-commerce website, and the system recommends you ketchup. So I have a question, is this considered good recommendation? Probably yes, because this is quite relevant to what you have purchased before. But wait a moment, so is this conclusive? Probably not, because when we are talking about shopping, so we need to make a shopping decision, right? But we have not seen the price yet. So how much do you want to pay for ketchup? $5? Anyone? No? Okay, that's wise. I would do the same thing. About $3? Anyone? No. Oh, just one, two. Okay, 3. Nice, it works. So how about $1? Okay, there are more hands. That's right. Okay, so that means when we're talking about product recommendation, price is actually a very critical factor for us to make the shopping decision. So let's compare to other kinds of recommendation applications, like movie recommendation, news recommendation, and music recommendation. So the major difference between product recommendation and these applications is that for application on the level side, so the content matters more. That means in most times the objective of the recommender system is trying to find items that will fit to users' preference. And the price is not a primary concern. Well, for the product recommendation, so things are more complicated. Besides the product has to match to users' need, the price has to be right. Otherwise, the recommendation is probably pointless somehow. So the key is like for product recommendation, 2 ingredients. First, right product. Second, right price. So the key is how do we estimate how much user is willing to pay for a product. So let me introduce an economic concept. It's called willingness to pay. So here's the official definition. So it is the maximum amount user wants to sacrifice to procure or buy a good or avoid something. So let me illustrate this concept using a concrete example. So let's say, willingness to pay is pretty like subjective, right? So let's say the sells a bottle of water, and you are going to. So how much are you going to pay for water? Well, that depends. I mean, depends on situation, right? So if you are in the desert, you have no water, you are going to die. You probably want to pay. If it were me, I will pay whatever I have except my life, right? So okay, let's say you want to pay $1. Man, this is really cheap. So okay, so you got the water and drink it. So you feel much better, and you ask the same question. So how much are you going to pay for another bottle of the same water? So this time, oh man, I have enough water. I would probably just pay $0.50, right? This makes sense. So willingness to pay. The point is that willingness to pay is a subjective matter. So it varies across people, and even for the same person, it varies with the situation. So why do we bother in estimating willingness to pay for the product recommendation? So there are actually 2 benefits for the consumers. So that means right product, right price. That's perfect, right? So you get the product at a reasonable price. You're happy. So you actually got a better shopping experience. That's good. And for the seller, so it can actually help to achieve higher revenue. So in order to understand this, let me illustrate using plot on the right. So this is a demand curve that is commonly used by economists. So let me explain this. So the horizontal axis is quantity demanded, and the vertical axis is price. So the general trend is that, so as the price decreases, the quantity demand increases. This makes sense, right? Because as the price decreases, you want to pay, so more people are willing to buy it. So in most cases, so the price is fixed. I mean, fixed means that it's the same to everyone, right? So the sales revenue is easy to calculate. So it is the area of this shaded rectangle. So we notice that actually there are people who are willing to pay more than $40 for this product. So what if we are able to identify this group of people and set the price same as the amount they want to pay? So what will happen? So apparently we are able to obtain more revenue as much as the area of this upper triangle, right? So likewise, we can do similar things to people who are willing to pay less than $40. So again, we can get extra revenue. That is the area of this lower triangle. So in theory, if we can customize the price on an individual basis, so we are able to get a lot more revenue than current like pricing strategy. This is amazing. I mean, for sellers. So how to estimate the willingness to pay? This problem has been studied extensively in economics and marketing research. So the existing approaches can be roughly classified into 4 categories. So I'm going to briefly introduce each of them. Category number 1, direct survey. So this is straightforward, right? The experiment practitioner just pick a yellow book and turn some pages and pick phone number and dial the number and ask, dude, how much you want to pay for this shampoo, right? It's very straightforward. So usually they will, they pick subjects with like diverse like attributes, like that change, the varying with like demographic information. So by doing this, the experiment practitioner is able to learn a regression function from user information to willingness to pay. Category number 2, transaction data. So this method uses real transaction data. That means like transaction data from Walmart or other supermarkets. So the way is like they can predict users' willingness to pay based on users' past transaction records. And category number 3, this is called choice-based conjoint analysis. So this category method is a little more complicated than previous one. So the subject will go through a list of questions, and each question is a choice question. So let me show you an example. So here the choices are different products. I mean, they are different in brand, processor, memory, monitor, and price. So the subject is instructed to identify one product they prefer to buy. So at the end of the experiment, so the practitioner will end up with like a list of records about users' choices, and they're able to learn users' willingness to pay based on the responses. And category number 4, so this is auction-based methods. So there are mainly 2 approaches. First is called weekly auction. Probably you guys are familiar with this auction method. So it works by first the sealed auction. So each bidder will raise the bids, and they don't know the bids of other bidders. So the winner will win the product by paying the second highest price. So another auction category method is BDM. So this is actually will be used by our work. So I will explain it in detail later. So what are the problems with all these existing approaches? So let's look at it. So for the direct survey, apparently the subject has no incentive to tell you the truth, right? They can either understate the price or overstate the price. They have no incentive to tell you the truth. So the data collected in this way are not reliable for building a model. And for transaction does not suffer the same problem as direct survey because data are real. They're real. But the problem is that the transaction price is only a lower bound of a user's willingness to pay, right? Let's say a user purchase a shampoo at $10, so the user probably is willing to pay more than that. And for this conjoint analysis, so it has similar problem as direct survey. So user still has the subject still have no incentive to be truth telling. So and for auction-based approach, they are very incentive compatible. That means the subject has the incentive to be truth telling, but its problem is that it's not scalable. It's not scalable to a typical e-commerce setting in terms of a large number of items and a large number of users. So estimating users' willingness to pay faces two challenges. First, the mechanism must be incentive compatible. That means you have to ensure all the subjects will be truth telling. Otherwise, whatever they say doesn't matter, right? So, and the second challenge is scalability. So that means your approach must be able to scale to an e-commerce setting that can handle large number of items and large number of users. So what do we do? So in order to overcome these challenges, so we propose our own approach to elicit users' willingness to pay. So the objective of our approach is to elicit users' willingness to pay in an e-commerce setting. So let's see how it works. So first, our approach uses bidding combined with lottery procedure. So we use BDM to get a multiple product bidding for a single user, and also we use lottery to get more more data samples with a relatively low cost. And with the data collected, we are able to modeling willingness to pay at an individual level. So this is done by training a regression function on user and product features. And we are able to predict willingness to pay on unseen products. And lastly, and the most exciting part is that we are able to customize promotion rate based on individual basis. So we actually can set the price so that the seller profit will be maximized. So this is an overview of the experiment flow. So let me explain each of the steps. So step one. So at this step, because when the user comes to our system, we don't have any information about the user. So the purpose of this step is we want to know what is the user's interest, and so that we can recommend some relevant products. So the first step is that user will search products on our system. So this is pretty similar for user visit our e-commerce website, right, and start to search what they want to buy. So, and the second step, so user is asked to rank the product selected in the first step. So the purpose of doing this, we want the user to reveal the preference. And lastly, so the system will be able to generate a list of recommended items based on on the user on the products user provided in the previous steps. Okay, so after step 1, user will see a list of recommended items. So now user is going to bid from the recommended products. So bidding means like user will find a product they like and specify the name, the price they are willing to pay for in order to get that product. And the user needs to bid at least 5 products. The reason we are doing this, we want to collect as many data points as we can. So only one of the bidded products will be randomly selected for BDM bidding. So I mentioned the BDM, but I have not explained that yet. So let's see how it works. So BDM mechanism was proposed like 50 years ago. So it's named after inventor's name. So actually the way it works is fairly simple. So first, given a product, the subject will bid a price for that product, and system will randomly draws a price from a certain range. So now we have 2 prices, right? One from the user and one from system. Now we compare user's price to system's price. If user's price is higher than the system's price, so user will be able to buy the product as a system price. So let's look at a working example. So let's say the subject is bidding the shampoo, right? The shampoo that worth like $12. So okay, so the subject bid $10, and the computer generates like $80. So clearly, user's price is higher than the computer's. So user will be able to buy the product at $8. So user can take different strategies to name the price, right? They can either underbid, that means the price name is lower than the willingness to pay, or they can overbid, the price is higher than the true willingness to pay, or they could be just truth telling about the willingness to pay. And it turned out the best strategy is be truth telling. So I will skip the mathematical details here. If you are interested, please refer to our paper. So step 3, lottery. So we will run a lottery of like $200 cash when the total number of subjects reach to 200. So the winner of the lottery will receive $200 cash if he or she fails as a BDM bidding step, or he or she will receive the product at the system price plus the cash remain. So is there something wrong with this approach? So you might wonder, so will the subject tend to underbid the products as they have multiple bidding chances, right? They can take advantage of this rule. So actually it's not, because we only want the bidded products to be randomly chosen for the BDM. So we can prove that. So it's still user's best strategy to state the willingness to pay truthfully. So step 4. So we have collect some bidding prices from the previous step. So now we're able to train a regression function. So the input for the regression function is the features we extracted from the previous steps. So here we use 9 features in the paper, and I list the most influential ones here. So for example, brand popularity and whether users switch the brand. So, and also Amazon's original average rating, and the promotion rate. So on the right-hand side is user's bidding price. So we learn linear regression function between these two sets of quantities. Okay, so we are able to predict users' willingness to pay. So we can do more. So we can actually personalize the promotion. So to do this, we first model as willingness to pay as a Gaussian distribution. So its mean is given by the linear regression function, and the variance is directly from existing training samples. And so in order to find the price point that will give the seller the most seller profit, so we try to optimize this function. So C is a production cost, which is known, and T is a quantity we want to optimize the price point. And here this accumulative probability is the probability user will buy the product if the price is T. So this can be optimized by using some numerical optimization algorithms. So let's look at the experiment. So let's first look at setting. So first we build an e-commerce website that is very similar to Amazon.com. So it hosts about 120K skincare products. The reason we chose it because skincare products are consumable and more likely to be repurchased and easier for us to recruit subjects. And we provide a product search function, so that is very similar to what Amazon has. And also we actually hire subjects from Mechanic Turk. It's a crowdsourcing platform. So it takes about 10 minutes in average for each subject to finish the experiment. And they will be paid about $50. This is based on the hourly rate. And we also use the recommender system for generate the recommended items. So we just directly using the one offered by Amazon. So it's like. So BDM sounds very intuitive and incentive compatible, but it's actually not intuitive enough for like a regular person to understand, you know. So actually there's like a study showing that. So this is called a frame misconception about the game. So they tried BDM in some like a controlled environment, and it turned out the subject actually did not use the optimal strategy. So in order to avoid this issue for our experiment, we actually run some training for the subjects. So we explicitly tell the subject that your best bidding strategy is be truth telling. And also we provided an emulator, BDM emulator, that allows users to tinker with different bidding prices, and they will see the outcome. So they will get a general idea how this works out. And also we run some testing questions. So we just make sure the subject understand what's going on. So we filter the subjects who failed the test. So we further sanitize data by doing this. So like we remove records with bidding price, let's say 10% or 2 times above product price. And also we remove subjects who finished the test like within 5 minutes. And also finally we ended up with a very small data set, only 54 subjects and around 340 data points. So how do we evaluate the proposed approach? So we did it by 2 metrics. The first is root mean square error. So this is very common. It's commonly used in most of the existing recommendation algorithms. And second, we use the seller profit. So this is very practical and is very interesting to the marketing practitioners. So here is how we calculate the profit is straightforward. So, and here is the experiment result. So we compared 5 algorithms. The first 4 are the baseline algorithms. So, and the last one is machine learning based, is our approach. So they are like the baseline algorithms are like Amazon original price and 90% uniform for applied to all the elements and 80% and also 0R. This is very baseline machine learning algorithm. So it uses mean of the training data for prediction for the testing data. So just look at the result. It shows that our machine learning based approach is superior to the baseline algorithms on each of these each of the settings. So okay, I forgot to mention. So here is because we don't know the production cost, we just make assumptions. So it's like we assume like the production cost is like 10%, 20%, and so on. And we evaluate the profit under these assumptions. So we can see that the linear regression is statistically better than the baseline algorithm. That means so personalized promotion does work. It can help improve like seller's profit, just as I mentioned in the earlier of the talk. Okay, so to sum up, so we propose an approach that is able to elicit users' willingness to pay in an e-commerce setting. So it's so we use the BDM bidding strategy and lottery mechanism. So it proves to be incentive compatible and also is very costly efficient. And finally, we are able to personalize the promotion and to get a higher seller profit. Okay, so I think that'll be. Thank you.
So there is one question. Well, I can give you my microphone. It's easier.
Hi, very interesting research. Thank you. You know, I could say what I'm going to say as a question, but I'll say it as a comment because I really mean it as a comment. You know, I work for Amazon, and I can tell you that Amazon doesn't do this sort of thing. And the reason is simply that we optimize for the long term and not for the short term. If you do this, then you may make higher profit off your customers in the short term, but customers are going to be upset, and you're going to lose customers, and you're going to go out of business.
Thanks. Thanks for the comment. Yeah, actually, yeah. So optimizing now for this piece of research is more about like how to modeling users' willingness to pay to prove that there's actually a way to do it in an e-commerce setting. But as you said, yeah, this is probably it's more beneficial for short-term, like short-term benefit. So I agree. Yeah, probably there will be more work to do for optimizing the long term. You know, like when do we run the promotion when not? So that probably then another subject. Actually, that is my part of my thesis. So I'm trying to work on that part. Thank you very much.
So I think
I have a quick question. So you rightly mentioned that there are different bidding techniques, and one of them is the Vickery-Clark-Grove mechanism. So do you have any particular rationale why you are not using the Vickery mechanism, because that is mathematically proved to be incentive compatible?
Yes, that's a good question. So why we are not using Vickery in the e-commerce setting? Think about the millions of products and the millions of users. So are we going to really need to set up this setting, like ask how much you want to pay for this shampoo, right? That's just too costly. So I mean, it's incentive compatible, but just probably not feasible. So I mean, auction could work for some like applications like hotels or airline tickets, but for most of the e-commerce products, it probably has its limitation.
Are there other questions? I can add a comment
Sure.
similar to that one, is that
Sure.
in some countries, at least in Europe, it is not allowed to do personalized price. So the same product has to have the same price for all the users.
Yeah, that's an excellent question. So actually, Amazon did that before, right? So and they run into some little problems. So probably it's like it's not a good idea to just like give different people different price. This is unbelievable, right? This will not work out. Users will be panic. But there might be other tricks to avoid this awkward situation. Like we cannot control the price, we can control the discount, and we can control the quota of the discounts, right? We can set different probability for the individual to get the discount. So user will not be able to sense that. So that will make things better.
Thank you. Other questions? Up there?
Man, gotta be quick. I'm really tired.
Yeah. Hey, nice question. Have a nice talk. Did you analyze the long-term effect of this learning?
Long term, I have not seriously started thinking about that. So long term is actually harder to capture. So there are like different stages. For example, for new users, if you want to promote a product to a new user, right? You probably want to apply some discount. Well, after user converted to this specific brand, you probably don't want to do that anymore. So yeah. So.
But so do you revise prices for the same customer or no?
So you are saying whether we show the same price for the customer?
Yeah. So if you have repeated interaction with the same
probably
customer.
not. I mean, along the temporal axis. So probably in the beginning, so just some marketing strategy, right? So this is a new customer that they're probably interested in our product. So the system is able to estimate how much user is willing to pay for this new product. So we probably use that information to set the price. So the user will get a chance to try this new product. After the user logged in, so probably there's not necessary to keep doing the promotion thing. Yeah, the price could be different.
Because economists have, of course, studied repeated interaction with users, and if you are not careful, then the rational strategy of people, if you ask them how much would you be willing to pay, if they know that you'll come back with other offers later, then the first reaction, of course, is no, that price is way too high. And if you, in many settings, depending on what your assumptions are, you can actually prove that you cannot benefit from learning if you have a hyper-rational opponent.
Yeah, that could be true. Yeah. So currently, our research is still very, it's done in very controlled setting. Still, it's very controlled, right? It's far away from the real scenario. So, yeah, we'll see. I will try to play with some real data to see what will happen.
So thank you again, Chief, for the talk. And I think we have to move all of us in the main room for the closing session. So thank you again, Chief.
Thank you very much.